Hello everyone, my name is Gregor Nolan and my video teammate is Thomas Leger, as well as our other three group mates, Benjamin Musgrave, Reed Miller, and Brandon Pinaran. In this video, we will take you through the brainstorming and design processes, as well as how to construct, use, and test our impact control experiment. I hope you enjoy the video and let us know if you have any questions. The ICE design project is a design challenge to create and record an impact. We had to invent something that would create, measure, and record data within itself as a system. For the customer request, in order of preference, the system design must create an impact, so have a collision of some sort, provide time-resolved acceleration, velocity, displacement, and force data, and that's giving each data over the time of the experiment. It must be easy to train a novice user so they can conduct good experiments off of light training. A high signal to noise ratio, so we need to measure what's important and minimize any possible disturbances that could skew the data. It must have at least 10 data points and one measurement pulse, but the more the better, to ensure a good, accurate data with high quality results and no outliers. And it must match peak signal impact magnitudes across all tests to within 5% of average values. And this is important for the consistency of the experiment because it shows that it is repeatable and gives similar results for all different types of tests. Before we could get into designing anything, we had to break down the system into an objective tree to truly see what we needed to complete for this project. The system could be broken down into three main categories, being accurate, user-friendly, and data collection. These three functions could be broken down further into sub-functions and sub-sub-functions. Breaking the system down into functions allows us to see the big picture and how each part contributes to the final product, and it makes the project itself look more manageable. The next step for our project was to create a house of quality to ensure the best result, as it helps us to rank importance and see what needs to be prioritized in the project. The first box is the what's, which includes the functions and constraints of the projects against the who's, which is the customers. We rank them by importance for each who by having one equal the most important and going down the number scale, where the larger the number, the less important for that who. We also had allowed ties for importance. We then totaled them together by row to see what the overall most important thing was, and the smallest number being the most important. And in this case, the most important was to create an impact for all who's. The next column is the what versus the how's. This relates the engineering specifications to the functions and constraints through a use of three numbers, where 0 is not related, 3 is somewhat related, and 9 is directly related. We also totaled these numbers together, and it shows what function or constraint correlates to the overall project the most. In this case, it was the accurate data followed by measuring time. The last part of the house of quality compares the what's to the what's by the use of ones and zeros, where 1 is more important than 0. This compares the what's to itself to show what to prioritize for the project. One of our alternative concepts was a pendulum design. In this concept, we would swing our data collection device from a set location and let it run into a foam cube for impact. While it would have worked, it most likely would not have had enough data points for what the customer originally wanted. A second concept was a spring-loaded slingshot device. In this mechanism, we would pull back a loaded deck and compress a spring, and when released, the spring would push the cart forward on a rail into a foam cube. This design looked promising for its consistency, but would require us to get materials from outside of class, and the spring could experience wear and tear. Our third design concept was similar to number 2, but instead uses rubber bands to slingshot the deck on a sliding platform into additional rubber bands. You pull back the cart, which stretches the rubber bands, and when released, the cart shoots forward on a low friction surface into other rubber bands, which slows the collision. To decide on what concept to choose, we had to create a decision matrix to weigh all of our options. In this, we ranked the functions versus the functions by how many times more important they are than one another, and then take the geometric averages of them. We also showed the normalized criterions for them. These values allow us to take an outside look at all three concepts and choose the best one based on numbers, which proves the correct option. Using this decision matrix, the rubber band slingshot method came out on top. Because the rubber band slingshot concept won in the decision matrix, we came up with our initial design, which includes a small box that houses a rubber band going across one end and a sliding cart with rubber band slingshots attaching to poles at the other end of the box. This way, when the cart was pulled to the back of the box, which is the same location every time, which is good for repeatability, it stretches the rubber bands connected to the poles, and when released, it shoots forward into the rubber bands at the other end of the box, creating a collision. Once we had our design chosen, we had to begin building it, and during the build process, we had to iterate and change several parts of the system. The first thing we built was the housing for the slingshot. We cut out pieces of white foam for the floorboard and the walls. Next, for the back wall, we cut out a small hole so we could be able to grab the cart from the outside and pull the back cart to the back to the same location every time to ensure repeatability and good data. Once this was built, we were able to start working on the other aspects of the impact control experiment. Next, we built a large cart out of popsicle sticks, but after deliberation with teammates and slight testing, we decided on using a small frame for the cart so there was less of a chance that the car ran into the walls. After we had the frame for the cart, we tested different sliding methods for the cart so the cart would have the least amount of friction against the floorboard. We first tried just the frame of the cart against the white foam cardboard, and then placed the white foam on the bottom of the frame and tried the white foam against the white foam, then tried regular cardboard against the white foam. Next, we tried electrical tape on the white foam floorboard. Nothing was working as well as we wanted to, so we switched gears into trying to push the cart on top of rollers made out of straw. We liked this idea, but there was a much higher chance of the cart running into the walls if any of the straws went in the wrong direction. Then we had the idea to line the floorboard with flat popsicle sticks and put regular cardboard on the bottom of the frame. Once tested, this had the least amount of friction, so we went with using it. Finding a low friction way was very important for us, as if the collision was too fast, we would not have had enough data points for what the customer needed. After the sliding method was chosen, we were able to finish the cart. We raised the frame of the cart using 4 small pieces of white foam and then placed the regular cardboard on the bottom. We glued everything together and then added a tail to the cart so we could grab it from the hole in the back wall. Lastly, for the cart, we added the vertical uprights that the rubber bands would attach to for the slingshot. After the cart was done, we added 2 vertical popsicle sticks, one on each side, to the open end of the housing. These popsicle sticks would serve as the place to hold the rubber bands that would create the slingshot and also cause the impact. One major problem that we encountered after completing the design was that the housing system was too weak to support the rubber band slingshot. In order to fix this, we added small triangle supports on the walls to help them stay sturdy and upright. And we added popsicle sticks running horizontally on the outside of the walls to prevent any bending that the foam might have experienced under tension from the rubber bands. For our materials, we used popsicle sticks, rubber bands, styrofoam sheets, hot glue, and cardboard sheets. We only used materials provided to us by the professor, and it costs about $20 per system to create. So the cart is placed between the rubber band on the uprights using the vertical popsicle sticks that are attached to the cart. It is then pulled back all the way to the wall with the tail sticking out for us to hold on to. After the cart is in position, you click play on Firefox on the experiment recording device, and once it is running, you release the cart and the rubber band springs it forward until the cart comes into collision with the rubber bands on the uprights. After the cart stops moving, the experiment is complete and the data can be exported to be analyzed.
One of the ways we reduced the noise of the experiment was by reducing the total friction by iterating the materials we used for the floor and the sled. Reducing the total friction reduced the noise by making the sled smoother, causing there to be less disturbance and give cleaner data. More noise reduction methods come later in the video. To gather data, we used a phone app called Firefox. Firefox has many ways to record data using the sensors in your phone like the accelerometer, the barometer, and the thermometer. The program we will be using for this project is the accelerometer without gravity. When we run the experiment, it gives us data that looks like this. To estimate the total number of data points, we first need to find out how fast Firefox records data and multiply that by the duration of the impact. We did some research and found out that by default, Firefox records data as fast as possible, which varies from phone to phone. According to Apple.com, most of their phones record at least 100 Hz. To find the duration of the impact, we need to find the change in time, which is the final time when the sensor comes to rest, minus the initial time of impact. Plugging in approximate data from one of our experimental trials, we get delta time equals 1.4 minus 0.73, which is approximately 0.67. Going back to the formula, number of data points equals delta time times frequency, we get approximately at least 67 data points, which far exceeds the 10 data points that the customer requested. To process the data, we will be using a programming language called Java. There will be a link to our code and a sample dataset in the description if you are curious or want to learn more. First, our code takes each value in a file of all the experiment data from Firefox, and it makes a really long list of each value. It then sorts the values into two separate lists of time and acceleration. When processing the data, we noticed that Firefox recorded lots of tiny acceleration values both before and after the experiment when the sled was fully at rest. This caused our data to be slightly skewed, and when we integrated to find the final velocity was not zero. To fix this issue, we added a section of code that formats the data before and after the experiment to be ignored, which greatly reduces the amount of noise that is included in the data analysis. For any skeptics out there, this is not cheating or making up data. We are simply minimizing the amount of faulty data that is included in our calculations to reduce noise. After that, we used a trapezoidal Riemann sum to integrate acceleration with respect to time and added the new velocity data into a third list. Using the list of velocity values, we used another trapezoidal Riemann sum with respect to get displacement data, which went into a fourth separate list. To find force, we went through each value of the acceleration list and multiplied it by the mass of the sled plus the mass of the phone, because force equals mass times acceleration. Because this value changes depending on the phone's mass, the code gets the mass directly by taking user input each time the program is run. Once the calculations are complete, the program creates a new window on your computer and starts to draw graphs. The code automatically calculates the scale of the graph so that each tick mark on the side of the graph increments equally depending on the maximum value of the dataset being used for that graph. When the graph starts to draw the line, it automatically color codes the graph based on what part of the motion of the experiment is happening at that time. You can see that the black zone is before or after the experiment has begun. The light gray is when the rubber band is accelerating the sled towards the impact, and the dark gray is the duration of the impact. It detects these moments in time by seeing if the acceleration sign is positive or negative or zero. During the impact, the code counts each data point from the list. As you can see in this trial, it is exactly 67, which is the same as the predicted value we calculated earlier. To find out whether or not we met our requirement of being within 5% of the mean peak signal magnitude, we ran a bunch of extra tests and got the absolute maximum value of the acceleration data from each one. We ran some statistical analysis on this set of data to find out a bunch of things, but mainly that the mean was about 19.6 meters per second squared. We then analyzed each trial's peak signal magnitude to see if it was within 5% of this average value. As you can see, two of our trials failed the test. Our project only met the requirement about 84% of the time, which is not what the customer asked for. The customer asked that every trial was within 5% of the peak signal magnitude. To measure how easy it is to train new users, we needed to create an experiment. Using our friends and my little brother as test subjects, we gave them a demonstration of the experiment as a group, ensuring they all had exactly the same instructions. During each trial, the observer did not communicate with the test subject and only stopped the timer once the data seemed to resemble good data by looking at the graph. As you can see in the table, all of the test subjects' data was within 5% of the average peak signal magnitude of our original trials except for Sydney. It also took less than 4 minutes for each person to get good data, which is well below our engineering constraint of 10 minutes. To recap, we gave ourselves engineering specifications based on the customer's requested features. We then brainstormed and iterated until we agreed upon a final design that could achieve as many of the functions that the customer requested as possible. We were successfully able to provide time-resolved data by integrating the data from the sensors. We were able to prove our experiment was easy to train new users how to use by conducting tests and comparing their times with our engineering specification from the House of Quality, which was 10 minutes. We were able to create a high signal-to-noise ratio by iterating our design to reduce friction and by filtering out lots of static noise in the data analysis code. We also greatly exceeded having 10 data points during the impact event by using a weak rubber band, which caused the sled to take longer to come to a complete stop, which gives more time for the sensor to record data points. Unfortunately, we were unable to successfully match 5% of the mean peak signal magnitude in all of our trials, and we only were able to get it 84% of the time. This is not a huge deal, however, because this was the least important request that the customer gave us. We prioritized the first 4 requests more than the last one because they were more important. Please like and subscribe to my channel. Thank you for watching.